Okay, good afternoon again. Let's start this session. So here I will go through a very brief introduction, and then, as I said before, most of the work is going to be with about training a convolutional neural network in Imagenet. So here we are going to talk a bit about input pipelines. Yeah, input pipelines, and so we're going to see what input pipelines means, and then we are going to learn to work with TF record files. That so we're going to use that. We're going to do that with TensorFlow, same kernel that we were using before, but PyTorch doesn't support them natively. And later in the tutorial, you will use an external library called DALI, NVIDIA DALI. But yeah, so we're going to learn about TF record files, and then yeah, we're going to do a very quick tutorial on how to write the data. So in preparation for later for the big part of the afternoon. Okay. So in a setting like the tutorial later today with Imagenet, you have you know, as a user of Piz Daint or as a part of a group, you may be in the situation that you share a very large data set. This Imagenet has millions of images. You have a very large data set, and you, as part of a group, you might be doing a task with this data set that requires the data to be in certain format. Like, for instance, maybe you need the images to be in a certain number of pixels, like 24 by 24, or maybe you need 200 by 200. But maybe somebody else that is sharing the data, he needs the images all converted to grayscale and not in 3 channels RGB and so on. And then in practice, it's not it's not, well, in practice it's not practical. It's not practical to have a copy of this data set that is going to be over 100 gigabytes, I guess, for every one of the tasks that people are doing. And so it's common to have the data in the rawest position, situation as possible. Like this is what you're going to find today with Imagenet. I think this is a bunch of images, and all of them, if I remember right, they have different sizes, and they are. It's not something already made uniform for a particular task. Okay. So you may be in that setting where you have to share this. You have to process this raw data, and when you have to run it, when you have to do a training on this data, you want to have ideally this a situation like this one. So you have, let's say you are in a single node, and most of the training, the optimization, is happening on the GPU, and always you want to. So, sorry, there is somebody muted. If you could please, sorry, not muted. Could you please check the microphone? Mute.
What? Mute.
Okay, thank you. So in your work, for your trainings, you have to always make so to always strive for having the GPU always busy, always, never waiting for data. And when you are dealing with raw data, you want a setting like this one. So the GPU is always running, and then the CPU is going to be loading the data from the hard drive, and preparing the batch. And with preparing, I mean if all the data, if all the images, for instance, are different in size and you need them in a particular size, you can do this resizing. Or if you need to do a specific transformation, like cropping a piece of the image or changing the colors or something, all that that can be done in the CPU while the GPU is running. In all this deep learning software, like the library that you are going to see later in the tutorial, they have very sophisticated ways of doing this part of that is done in the CPU. And there are things like prefetching data, so in advance, that you have like 10 steps already in advance before the GPU needs it. So to make the setting the easiest as possible for the GPU to never have to be waiting for data. Okay. This is what we call input pipeline. So this kind of software or workflow that makes possible something like this. So opposite to this, what you really don't want, just to show it, is if you have a situation like this one, like the CPU is loading the data, and then the GPU is waiting for this, and then the GPU does an operation on the data, and then the CPU is doing nothing, and so on. So this increases the training size and the training time, and yeah, waste a lot of node hours in doing nothing. Okay, so in input pipelines, there are these three concepts that they are divided into these three parts: the extract, the transform, and load. This is what I just explained. So extract is reading from data. Sorry, reading from persistent storage from the hard drive. Then once it's read, the transformations are applied in general in the CPU, and then the input pipeline should load to the GPU the processed batch, so the GPU can work on it. Okay, this is very simple. So right now, then let's go to the notebooks, and so we are in the no, sorry, I get confused. I get confused. I'm sorry. This is not. We don't go yet to the notebooks. So let me talk a bit about TF record files. So the TF record file that I mentioned before comes from TensorFlow. It's a data format, storage format that was designed for TensorFlow. And these are the ones that they recommend to use, and the ones that their APIs for input pipelines are tuned to use. Okay, and the data is saved in a record oriented format. It's something similar to JSON, but in binary. So like JSON, you know, it looks like a Python dictionary that you have an entry like image1, and then some you would have, like, let's say the binary of the image and some metadata, and then so the next image would be image2, and then some metadata and the binary of the image, and so on. And in TF records, this kind of JSON units dictionaries, they are not JSON. They are something called protocol buffer. That is something that also comes from Google. But you can imagine that is very similar to JSON. It's like blocks of units of data, and this is different. That's why it's called record oriented. Different to something like like if you save a NumPy array, that you get a whole array, all the block of array is completely a data stream in hard drive, or HDF5 files. That is something very similar. You get a whole array of data in a continuous binary. Okay, this one you have like these entries for every image or every element of data that you want. And so that's it. And this is some best practice for storing data, and mostly this is more important when you have very large data sets like Imagenet, for instance. So the first, one of the most important things is to avoid storing the data as multiple small files. Like for instance, again, Imagenet is millions of images, but if as you get it by default, if you get it from the original source, you will get a lot of JPEG images, and you have all this JPEG, like millions of JPEG images, and you put that on scratch. Your training is loading on that is going to be very it's not going to perform well. It's going to be very slow. Plus that it may disrupt the file system and really create problem in the whole computer for all the users. So this is very important. Avoid storing data as multiple small files. Another point is to divide, if you have very large data sets, like many gigabytes or terabytes, to divide it in TF record files of about 150 to 200 megabytes. This one seems to give a good ratio, easy to load and easy to deal with, that you don't have as many files as single images. Or in the other hand, having a very huge file is also it's not very convenient, because it's very hard to load images from something that large. So this size is 200, around 150 to 200 megabytes, give you a good compromise between the two options. Okay, if you have small data sets, so in this range, if you convert it to TF record, there is no need to separate it. 200 from this size that we gave here to 1, 2, 3 gigabytes, it can be handled easily. And one thing that can be done in advance is when the data can be uniformly distributed over the TF records, and like that you can shuffle when you read, when the code, the input pipelines reach these TF records, they can be shuffled around the file itself, and you add an extra level, let's say, of shuffling that will help with the internal shuffle of your that your input pipeline will do. Okay, and also very important as this one, the first one is to always save the data in Scratch. So, for Piz Daint, obviously. And yeah, this is the place. Reading data from home or projects or store, besides they can create problems in the computer, it is very low performance. It won't give you the performance that you will get in Scratch. And now we do go to the tutorial. So we go to TF records, and inside there is only one notebook, read and write TF record files. So we are going to get two images that we have there. There are two cats, and we're going to load them. We're going to save it in a TF record file, and we're going to read them. Now, so here, so these are the cats. Let me start the kernel. So I will give a couple of minutes for everybody to have the notebook started. Okay, so clear up. Okay, so if everybody is ready, we can start. So the idea of this notebook is so we have, as I said, you have two images here inside of. You come here inside of images. There are two JPEG images, and we're going to we're going to load them first. So these two cats, so they have different sizes here, you see, and they are so they are in three channels. So one for each color, okay, and that's why they are in color. And so and this one is something, this kind of workflow that we're going to do now is something that you would do if you want to transform your data to TF records. So let's say that I don't know, any kind of data that you have, this thing should be valid. If you have arrays or something, you can the idea you can just copy and paste the things that we're going to use here, and use it in your own scripts. Okay. So the first things to write TF records is to define these three types here. This one, the last one we don't use, so we use this only these two. So we have things that that will go in the TF record as this that we call byte feature. We have things that we are going to put in the TF record as int 64 features, and there is also float features. Okay, so these are the three types of data that you can save in this file. In bytes, they would be for strings and byte types, like binary data, right? So if you have a metadata or something, you can pass it as a byte feature. And for that, so this the only thing that it does is to wrap this TF train feature. So TF is TensorFlow, of course. And in the byte list that will go to the TF record, this is again this long thing, and inside value you pass what you want to pass. Okay, that's why we use this wrapper, because this is a bit long to deal with every time you have to write something. So int feature, it will be exactly the same. So this one we can put booleans, int 32, so any kind of int, of integers. This enum here, I don't remember what is it right now. I'm sorry, I will have to go back to you on that. And this line is the same, but instead of passing this by list, you pass int64 list, and here int64, and again. So every int that you have, and in this case, these images are ints, just values of color. We pass it as int64. And same thing here for float, both float 32 and float 64 types. Okay. And then check this one. So for instance, if we have for this number 4.5 is it's a float, we pass it using the float feature, and so it looks something like this. So it's like similar to JSON. It's kind of a dictionary kind of structure with value inside that you put and the number. Okay. And to the file that is the other line, it would be something like this, just a line. And the file would be, if you have like different numbers that you want to put together in a file, it would be one line for this one, the other one, the other one, forming these records that I was talking about. Okay. Okay, now let's write the images. So the writing the images is always, or any kind of data, actually, is always the same. So the steps are, so create a TF record file, then loop over your data. In this case, is our two images, and then write one by one. That one we know because TF record file is a record-based file system. Okay. And then, yeah, the idea is to create a feature dictionary that we're going to see in practice. And then we put the keys that we want to save, similar to JSON. And then you pass inside this dictionary the values wrapped with these things that we saw before. Okay, and then yeah, the final thing you create with that, you create an example, and this is what is going to go to the TF record file. So for instance, in this case, so we can run here. So we just created it here, cats TF record. And so we loop, no, sorry, we open the TF record that we want, that we call cats TF record, and then we loop over the image. I think, sorry, I think I can put this a bit bigger for you. Increase text editor console. No. Yeah, like this. Sorry about it. I think it was too small. Now it's too big. Okay, so we look for over the image in your data, wherever the data is. So we have our images. So here we define this thing. Sorry, it's here. The path to the image and the label. And so we read the image with anything that you like or whatever however your data comes from. And then so you create this TF example that I mentioned before. And inside of the TF example, you create the features dictionary. And here you put, so we want to save the thing in this case that would help us to decode it back. Because as you see, with this binary, we need to pass information how to decode it, because otherwise we cannot recover the whole image. So we need the height of the image, the width, the image itself, and the label. So these three is just metadata of the image, and this is the image itself. So height is a number, it's an int, the number of bytes yeah, of course, bytes, I guess. The number of pixels in this side with the number of pixels in this side, those are ints, so we use it like this. And the image is we serialize it as a string, and using some functionality, external functionality from this IO EM read. And since it is a string, we serialize it. Sorry, we use the byte feature. And same for the label, that is already a string. We pass it as a byte feature. And that's it, and we write. And this very thing here, you can just copy and add it in any kind of code, of data that you want to transform to TF record. Okay. And yeah, that's it. Here, this is what the next one of these examples will like. Is similar to what we saw before. So we have the features, and the features have a feature inside, byte feature, value, byte list, and has here this label, and then you see another how's it called, a float example that we put. It looks like this, and yeah, that's it. And this is the serialized, what would go. So this is like human readable, and this is what is going to be serialized in the TF record. Okay. And that's it. So it's not particularly complicated, but you see, it needs some. You need to know how to do it. It's not like data.save as TF record. It has some work to do, but it's only boilerplate. You just have to repeat all these things so anytime, but it's very simple. Now to read it. So here we have the steps. To read it is also not simple, but it's also again boilerplate. The thing is, you have to use something that will loop over the TF record file, so that you can pass the TF record file and can let you loop over it, and that can be the TF data API of TensorFlow, or the NVIDIA DALI library that you will see later in the tutorial. And these things, they have a map functionality or something equivalent, where you can pass a decoder. And in this case, it's going to be like I was talking before, that the data is going to be read, and while the training is happening on the GPU, the CPUs are going to be decoding the TF record. That would be something that the load and transform part. Okay, and the decoder, it looks scary, but it's very simple. So, the decoder defines this single example where it's going to pass the batch that you're going to give, and here you can specify the same features that you know that your data has, and it's going to extract it. And instead of passing these wrappers that you used to write, you pass the feature type that is going to extract it, and then you say what they are. So this one, a height, we know is in64 and in64. The width, sorry, the image is a string, and the label too. So once this passes, so it needs to be casted to the types that we want to use afterwards in the training. For instance, this example width, we need to cast it to TF64, the height the same, the image as unsigned int, and the label to string, and we can here compose this one. It's not really part of the decoding, and it gives image and label. So now when we do this looping here, so this is a warning, I'm sorry. Oh, I didn't save it. That's it. This is something that we just defined, and it's not really running. It's just we don't just declare it. And in this data set now, when we loop with it, we recover back the two cats. So I see there is a hand.
Hi, yes, Rafael. Yeah. So yeah, this could be used also for open graphs, because when I see in the decoder, there is this fixed length feature, but for example, for graphs, perhaps we could have a variable length of feature, so a different number of nodes or edges.
But what would be the data, like different graphs, or yes, I guess.
Oh, well, yeah, the different, well, like one image converted to graphs, and then in every image we could have different number of graphs and edges.
Yeah, but if I understand right, I think yeah, I think in that case it would be similar to this one. Well, I don't know. You tell me. Because here we have two different images that they have different sizes, and I don't know why it's called fixed length feature, but this doesn't mean that everything in your TF record file will have to have a different a different length or different number of bytes. This is just the name that it has, but you can save things with any kind of shapes. If I don't know if I'm replying to your question, or I'm a bit off.
Okay, yeah, I have to think. Thank you.
We can continue afterwards in the chat if you want. Sorry. And okay, so that's it. This is how you write and decode back image from or general data from TF record. And just to finalize, the very good thing that advantage of doing this and going through all this trouble of writing such a long this writer function and the decoder. The advantage is that once you write it on that, you can use, for instance, this NVIDIA DALI library, and all the logic that you need to create something like this, opposed to something like this, you are going to get it for free, because these libraries, they are tuned to work with this kind of data. That in the other sense, if you save it in a custom file format, then you will have to take care of doing the decoding or the reading yourself, and you may not get the same kind of performance that these libraries that are really very well done can give you. Okay, and I think like this. I finished my introduction, and you can continue with the rest of the tutorials with Enrique. But thank you.
We're gonna now talk about Imagenet just as an example. I guess most people are familiar with it already, especially if you have done any deep learning before. But anyway, we just thought we'd just go quickly through it just as a motivation as well. And we're gonna use TF records as we were saying before. But I think trying to answer David's question as well, it's a very much a generic tool. Like you decode your raw data there and you decode as you want, right? So you can put any binary data there. But anyways, about Imagenet, right? Imagenet is actually quite an old data set, and I guess I think it's from 2011 originally. And originally actually had more data than people use nowadays. It was 14 million images about, and it had these 21,000 labels. But then what is most famous is actually a subset from 2012, which they basically took the most common 1,000 classes. So it's way more balanced and nicer to work with. And they created an open challenge for people to play with. And yeah, in 2012 already, well, actually, I think the challenge is from 2011, but yeah, the subset people use is the revalidation that they did in 2012. And that's when as well, people actually started using deep learning for that. The famously AlexNet was then actually won the competition in 2012. And you see, before that, most people are using like classical old school computer vision, with like feature extraction and supervised vector machines on top of it. And then AlexNet came, and you see the error is so much better. It's a complete outlier in the competition, right? And after that, everyone basically started using deep learning for that, right? But the biggest catch, actually, if you get the AlexNet paper, it's all about running the model on GPU. It's nothing really about the model itself. It's just the harder challenge. They are more complicated because the deep learning model is actually quite simple, as we saw, right? Just a bunch of layers, convolutional layers on top of each other with some nonlinearity, and that's pretty much it. But yeah, it's a problematic, obviously, if you have to run a large model over these millions of images. It's already complicated. Nowadays, the GPU is much better than 2012. So it's much easier to do it today. But yeah, it's still a challenge. As you can get this graph from Papers with Code, which is a really nice website if you're not familiar with. And you can see here how people are solving that with SIFT and the old school computer vision stuff. And then we get AlexNet. And it still kept evolving, right? Until even recently, we almost getting to 91% now, just a few months ago. And although most people from this point on are actually using a larger data set. They're not using the original data set per se. They pre-training on many more images, right? And that's the whole point of deep learning, right? You can have larger models with more data and they generalize better and so on. And Imagenet got really popular as well because he allowed this transfer learning with pre-trained models. You can download the pre-trained model in Imagenet and then use it for any kind of image. Even if it doesn't even look like the image from Imagenet very much, it still transfers quite okay in most cases. So that's what made deep learning very popular and actually popularize the thing and make it accessible for a lot of people, right? So you don't have to train the whole thing. You can get the pre-train and train on much less data as well. So that's the other side. If you haven't seen the data set, it's just like random image from the internet, and it has these 1,000 labels, which are also kind of random. There are 117 dog breeds in the middle of the thing, and stuff from fish to toilet paper and mushrooms and everything, pizza, yeah, and so on. And yeah, just going back to the TF records, because we have all these images, even just 1 million images, if you have to read them 100 times, that's a lot of reading, and we expect random access the whole time. So the trainer, the algorithm that's actually training the model, doesn't actually know which image it has to read, right? Each epoch is completely reshuffled. And because of that, it's very hard for the file system to actually handle these requests in real time. And if you have SSDs, it's easier, but it's still an issue. Like you still have to be aware that if your input and output pipeline is not well made, you're actually starving your GPU and you're just wasting compute for no reason, right? Just waiting for the disk. And yeah, in Piz Daint, Scratch is fast, but if you're running a model with lots of nodes, or if you're running several models at the same time, it still can easily become a bottleneck. So we definitely recommend using TF records. The main advantage, I don't know if it's clear yet, is that TF records don't actually have an order. It's just really a list, like Rafael was saying, it's just a list of dictionaries pretty much, right? You have these key value pairs in your features, and they're basically like the key and then the content of the feature, and you have a list of that, and the file doesn't even know how many images you have within the file. So when you open it, the data loader, the TF data loader, doesn't even know how long is the file. It doesn't care, because it can read the beginning of the file, the first image, and give it to the trainer, and then read the second image, give it further, and it can read incrementally from the file, and it just has to track where in the file it is right now and just keep going on it. So it's much faster, and the file system knows exactly what is the next image that's going to read, right? So it's much easier to cache and to send it on through the network. It's all much more affordable for the whole system, right? Okay. So let's do another notebook. If we go now to PyTorch training Imagenet, the first notebook you will have is still in TensorFlow, sorry for that, but it's okay because it allows you, yeah, as we were saying before, TF records are actually protocol buffers, right? Which is a completely generic serialization protocol. It has nothing to do with TensorFlow whatsoever, and it's used for a lot of stuff, especially in Google, but all over the place. Internet is very popular, but you could actually read and write it without TensorFlow. It's just easier to use TensorFlow. So yeah, let's do another little quick exploration of the dataset. So we offer here at Piz Daint the Imagenet in the Scratch dataset. It's under this path, and you got the validation and the training set. Did I run this before? Yep. So you see here we have 128 validation files, and there's also the train, which has 1,024 files. You see it has this weird naming here, but well, that's the original. I use the original script from Google, so for the sake of it, and which creates this number of files. And it has a pretty reasonable file size for the file system. And when you read it, it's basically what you guys saw before. You have these features here and then the value attached to it with a specific type defined in protobufers. And there are the options from integers, floats, and byte lists, right? So this is actually the image itself in JPEG, right? Or whatever format you chose to, but here was all the images are encoded in JPEG. Actually, in the original dataset, some images are in PNG, and they are converted to JPEG as well to facilitate the opening. And if I go to the end of it, so you got the whole image, unfortunately. Sorry, there is more metadata from the file still. You see the file name and the format, the height, and the width as we saw. All right, and decoding that in TF2 is actually quite easy, right? As we were seeing before. You can create this little decode method and then just use a TF record data set and map that decode method into it. And this map is actually this function is gonna be run on each one of the examples and return an image and a label back, right? So you need to know the features here, but you can actually open them using the example like that. So the metadata is in the protobuffer. The only information that the data set doesn't have, as we were saying before, is the length. If I get the length of the data set, sorry. That's interesting. Did I miss anything? No, sorry, it says length is 0. Yeah, okay. Yeah, I thought we would get a better, yeah, we should get no, it's rising in error. Okay, that's new. I think before you should just return zeros or -1, something like that. Yeah, so the data set doesn't actually know the length of the files it's reading. So the user shouldn't actually provide the numbers. So when you're running Imagenet and TensorFlow, people generally have a hard-coded number of the images, and they divide it to calculate the length of the thing. Well, actually, it does know when it's finished, so it's not that bad. And then, yeah, you can easily grab the images. We could do the same with the training set, obviously, as we were doing before. And they'll give you a different set of images, right? And yeah, feel free to play a bit with that, but it's reasonably fast. The TF data is actually quite powerful. You could actually use, yeah, that's the thing. So in PyTorch, it doesn't have native support for TF records, right? In theory, you can use TF data to do that. You just have to convert the images to torch tensors. You can do that even without copying the data across. You can just map the intrinsic data of the tensors from the TF to PyTorch. But we propose to use NVIDIA DALI instead, because it's actually quite powerful application. And then we can go to the next book, notebook. Let's close the first one. And so yeah, NVIDIA DALI is a library offered by NVIDIA, obviously. That actually allows you to do way more than just reading TF records, right? It has readers for all kinds of formats. You can read like NumPy's arrays directly, you can read videos, and it has some support for augmentation itself. And yeah. So yeah, the NVIDIA DALI allows you basically to do the same, right? To read the files, but from TF records.
Sorry, Enrique, just to interrupt. What about if we, because I didn't give any time for my notebook to play, and also for the Imagenet decoding. What about if we give like 10 minutes or so to
we could make a little break, yeah. Mm-hmm.
Yeah, for them to play with to have a look to the data inside of Imagenet, and then you continue. Is that okay?
Sure.
Okay, perfect.
Do you guys have any questions? Anyone? Anyways, I think there's a few threads going on here. Okay, so let's go back to 30. All right, I see you guys in a bit. So let's get back to it. As I was saying, the NVIDIA DALI data loader is very, very good for fast loading of TF records, right? There are other solutions for PyTorch around. but this is really where NVIDIA is pushing the limits on file access as well. They're using this for all their machine learning benchmarks, trying to get training as fast as you can, right? And they do have lots of very interesting features that you can explore. But anyways, let's get back to it. So basically, we're just listing here the files again in this notebook. We got the basic imports up here. And the one difference here is that DALI requires these index files. It's also required by other data loaders. But it comes with this little script that you can run in your data set and you generate these little index files by itself. It's no big deal. It's pretty well documented. I could add the link here for the documentation, but yeah, it's basically, I'll just grab one of the index files, which I listed up here. And if I call the head of it, so it's just the beginning of the file here, you can see that it basically has just some numbers, right? That's kind of weird, but the file only has 391 lines. And it's one line exactly per image in the file. And it contains the beginning of the image and the length of the whole record, right? So that includes the image in this case, and all the metadata, the annotations and everything. And then you got the second image and its length. So you always can add these two and get the next number, right? It's very simple. And this is just to help the loader to know exactly how many images it has in each file. And that will help us doing the sharding. Remember, when you're distributing the loads, when you're distributing the train across several nodes, we want to distribute the data as well. So that we only split in 1/n of the data on each node, right? And to do that, you at least need to know how many images you've got, right? And that's how they do that on DALI and other data loaders. I was saying in TensorFlow, normally people would divide that by hand, basically with a hard-coded number. But yeah, anyways, so once you have the index files and the TF records, we can use the DALI data loader. And I'm gonna present here only the PyTorch interface. He also supports TensorFlow and Imagenet, I guess other frameworks as well. Right, but in PyTorch, it's basically uses this wrapper on top of the pipeline, how they call it, and that's pretty much it. It's not very much difference from PyTorch to TensorFlow. Actually, it uses internally its own data type. I think they call it DL tensor or something like that, which is pretty much less like a Torch or a TensorFlow tensor. But yeah, it just has a raw data format that can be converted very efficiently. Anyways, it's the data loader. I have to warn a bit. It's slightly more verbose. It's not as nice as the TF data. I do like PyTorch way more than TensorFlow, but I must say the TF data is actually very well made. But anyways, DALI does have way more features than TF data already, and they keep adding more stuff the whole time. Every competition there is any NVIDIA on, they build stuff specific for their own new hardware, for the new data sets and so on. So I will not go through, there are several ways of creating this thing, but what I'm going to introduce here is basically a function that gives you data loader back. And we're going to give several parameters to this function, and then I explain just briefly what we do in each one of those. So basically we have here just the list of files, right, and the index corresponding to those files. And we can see here already that we have shard IDs. So shard is just another way people call on distributing the data, right? So it's how many times you split your data with. So if I have 8 nodes, I probably want to have 8 shards. Although there are some circumstances that people do is slightly different, but yeah, generally this is the number of nodes and this is the rank that you're using, right? And then obviously you got the batch size, number of CPU threads that we're going to use to read, and some image parameters that we're going to go over this later on. And it basically all works with this pipeline. the pipeline is already aware if you're running that on a GPU, on a CPU. Actually, yeah, I think there are some slides that I wanted to show before. Yeah, let's maybe talk a bit about the model itself, so we have more context, I think. So yeah, I guess most people are very familiar with CNNs, but anyways, I will just quickly say something about it. Basically exploit this translation equivariance, right? You have the shared nodes all over the filters. So for the model will be a series of layers. There will be always these convolutions, non-linear activations, then a polling layer, maybe undersampling, subsampling, and then another layer and so on, until at the end you flatten everything. Maybe there is a global average polling before, and then you have a fully connected layer and your classifier on top, right? But you have this concept of weight sharing with the convolutions that greatly reduce the number of weights, and it all comes out on the idea that the images don't really matter, like independent of their position, right? If you have a car on the left corner of the image, on the right, the bottom right corner, it's still a car. So, and that's the assumption that we take by this weight sharing and this filter, filters, the rolling filters, basically, that happens in the convolution, right? And there's also the idea that large filters can actually be decomposed in smaller ones. We're not gonna get much in detail into that, but just a basic idea. But yeah, these translation invariants doesn't really account for rotations, right? If you rotate the car, the filters are not gonna match anymore. And also doesn't really do color and luminosity very well, just to a certain degree. So data augmentation is a major topic on CNN, and in some pipelines, this is already integrated inside the data loader itself, right? Because as Rafael was saying, sometimes you want to do that on the CPU to don't overload the GPU and let the GPU just really do the model, which can be greatly parallelized. And the augmentation is a topic by itself, right? There's a lot of open source libraries around, and people use it as the training itself. It's really part of the model, pretty much. You can use it for self-supervised learning, just really saying that the independent of the augmentation, the image should mean the same. So you got these representation learning and metric learning and so on. And as we're saying, generally it's done in CPU, but some libraries actually support GPU as well. And that's the case of DALI. Corn is also a great library, by the way, and could also be used with DALI together. And as we saw before, Rafael was saying, we basically always have this pipeline thing going on where you have like several CPUs in the background doing the loading from the file system, the coding of the image, then augmentation. And then when that's ready, you can actually start the model training, doing the forward and backward pass, right? And in the case of DALI or Corner, for example, you can shift this augmentation into the GPU. That's especially useful for, basically if you don't have enough CPUs. Obviously, this augmentation can be done much faster on the GPUs. Well, like GPUs are made for graphics, are done extremely efficient on GPU. Now, let's go back to the notebook where we're sorry for the interruption. And as you see here, that we're talking about the pipeline, right? The pipeline from DALI already is aware of which device you're using, if it's a GPU or a CPU that you're running on, or if you have multiple GPUs on the same machine, which is not the case of Piz Daint, but you could have several devices here. And so the pipeline knows exactly where it has to send the data, basically. But the pipeline itself is gonna do exactly what we're doing with TF records, right? It has to read the files and decode them and run some augmentation if you want to, and then just get ready for the training, right? Normally that includes some resizing, right? So you can actually batch them together in a single tensor. Yeah, and we have this TF record reader. And as I was saying before, DALI also has readers for other formats, for video and even NumPy records. And basically in the reader, as we were saying before, we have the features here that we have to basically pass to it. It can't really work out it by itself. And those are the features that we're interested in, so it can actually ignore the other features as well. And we need to give them the type as well, right? Addition to that, we already have the sharding in the TF record reader, because it has to know which part of the files is going to read, right? I'm going to give it the whole list of files here, and it's going to work out itself which files it's going to read. There are several other options to do that, and this is the basic here, but I'm showing you some configuration that it's already quite fast, but it can be speed up depending on your specific application as well. Right. One other compulsory thing is for training, at least, is the post shuffling. As Raphael was saying, when you create the TF records, it's already a made up list of files. And if they can be shuffled already, but if you read these files always in the same order, they can compromise your training. So you also in TF data, you're gonna have a post shuffling. So we're first gonna fill up a buffer with 10,000 images and reshuffle, and we're gonna read from this random shuffle, random buffer, sorry. And this also supports prefetching. So, well, this is kind of obvious when you have a buffer like that, but you can also have additional prefetches after the buffer, right? So after the 10,000, it's gonna read another specific number of files that you give it, right? And this is very useful, especially if you're doing a single threaded reading, which is not going to be true for us, but also because the images have very different sizes. Some images might take much longer than others. So you kind of need this reading buffer going on, or you will compromise your reading. And exactly like TF data, we have here, the return of the reader is just a dictionary of tensors. And yeah, by getting the encoded image, this is really an encoded JPEG, right? This is not the RGB image. We still have to decode it. And DALI has some fuse decoders, you could say. They can decode the image and do some operation already. So in this case, for training, it's recommended using an image random crop. So it decodes the JPEG, but actually it only decodes the part you need from the random crop. We're not going to go through all the parameters, but it's basically the size of the crop and the area of it. And it has some additional optimizations they can make. If you know the size of your image is the max size, you can pre-allocate the memory. And the great thing here is that, well, I put this option so you can choose if your augmentation is going to be on the GPU or on the CPU. And we're going to explore a bit the difference on that, right? And for the decoder, you can't give it device GPU, you give it this mixed device, because it's actually reading from the CPU, but decoding on the GPU, right? And actually there's a parameter that allows you to actually mix up as well. So you can have part of the decode going on the GPU and part on the CPU. We're not going to go through that, but yeah, it's very interesting. But it only works on A100, I think, on the latest hardware. And then obviously after decoding, those images still have different sizes. So we have to resize them to whatever given size you have. I put some basic augmentation functions here, but there is a link to a large list of support augmentations as well. So here we have a uniform rotation of the images. And as I was saying, GPUs are very good to do these kind of transformations, this warping. And yeah, so we can exploit that if your model is small enough. If your model is really large, then you're gonna want to have CPU augmentation, right? What we're gonna see. Some Gaussian noise just for it, and then yeah, we're gonna just have initialize this random coin flip, they call it, which is basically just a Boolean, which is either 0 or 1 with probability of 0.5, right? And we're gonna use this later on this also fused function here, which does cropping of the image, the random mirror, depending on the parameter that you pass it here, and also normalizes it, right? If you've done any image training before, we generally normalize your data. Well, actually, any machine learning, basically, you generally standardize your data, right? You mean subtract it and divide by the standard deviation. And that's basically what it does. And if you recall before, we set up these constants up here. And that's basically what it's using, right? So this is the training loop, and the validation loop is slightly easier, simpler. So you're just gonna decode the images and resize them, and then come to the crop again, right? And it's not gonna flip it. So that's it. So you need to give the output to the pipeline in this slightly verbosely thing. This also allows you to copy them to the GPU already, even if you're still doing the augmentation on CPU. That can also reduce the bottleneck of the model actually having to wait for the copy of the tensor over to the GPU, which, depending on the resolution of the image you're using, it could actually impact your training, considering. And then the only PyTorch specific part of the code here is this last iterator, where we choose the last batch policy, if you're gonna drop the last images, or if you're actually gonna create a smaller batch. On validation, obviously, you wanna have all the data. On training, you don't care. You probably wanna make sure your batch size, your last batch is complete, so the gradients are always in the same scale. You're always looking at the same number of samples every step. So generally you drop, or there's also an option to fill with the first images of the next epoch already. Which, it's pretty, about the same, I guess, on training consequences. So, but you're free to choose that. They'll give you an extra batch per epoch, right? And yeah, that's basically it. So I don't know if you realized before, but the first line of this cell here, I'm actually just writing a file, right? I find this kind of useful when you're creating your, exploring your code as well, because you can already use these on your code later on. You're gonna be able to import this file and use those images, use this function, sorry. But at the same time, you have the code here on a cell, and you can quickly change it if you want to, right? And so here I'm just importing that file and that function, and I'm using it with the validation files, right? And just for testing, I'm gonna put a syntactic word size. So we're gonna only see 1/5 each. Yeah, that gives you 1,000 images, right, from the validation. And with byte size 6, so we can actually visualize the images. And let me just run all of this. And yeah, this should only take a few seconds, I guess, to go over the whole thing. And in this case, I'm using GPU augmentation, right? So we're gonna see on the GPU usage. That was a bit too fast. Okay. Well, that's still useful. Let's say we can see that the last batch here is actually smaller than the first batch, right? So during the loop, I saved the first batch, and we explain the last batch as well. But yeah, okay, let's grab more images. And that takes a little longer. And Okay, so you see, we're not actually using 100% of the GPU, because maybe because the batch is too small. That's a bit better, right? And there's not enough images, but yeah, it's able to utilize quite a lot of the GPU just reading images. The only thing that DALL-E is not very nice interactively, it actually doesn't clean up its memory very well. So if I create several GPU data loaders, it's actually gonna keep accumulating the data. I guess I should report that. But when you're doing a single use, it doesn't matter at all. And they might have done that on purpose to save allocations. Anyways, yes, you guys can play a bit with that if you would like. Please have a look on the operations on the DALL-E supported, and you can try to add some additional augmentation here if you want. As I said before, maybe you're gonna say you don't use images on your modeling, so you don't really care about Imagenet. But this pipeline is useful for any kind of applications that you may choose, right? First, TF records can hold any kind of image, arbitrary, and augmentations like Gaussian noise doesn't actually assume that the data is an image at all. It just adds the Gaussian to the tensor, right? The Gaussian noise to the tensor. So you can still do augmentation even if you're not using images. And yeah, so this works for any kind of data anyways. All right. I guess we can wait until 3. Okay, let's resume at 3, if it's fine with you guys. You guys have any questions? Okay. So if you also change the parameters for the GPU augmentation to false, and then you can actually see that the number of threads actually play a massive role here, right? As you do in GPU, it doesn't change that much the result, but obviously in CPU, you actually limit the number of CPU threads you can use. So it's going to be much slower, even to load the data set. However, if you just put 24 threads as well, it doesn't actually speed up further after 12 threads. You can see that it's using actually most of the CPUs now, but it's as fast as with 12 threads, although we do have 24 cores on these machines, right? So, and if you're actually doing this during the training, PyTorch will use some CPU. So if you starve all the CPU resources as well, you can actually make your train slower, right? So those kind of parameters, you should play a little bit around before launching any major job that's going to use a lot of compute time, or you're going to be wasting some of that resources, right? So yeah, it seems for CPU that you want to have 12 threads, and GPU that doesn't seem to change that much, but anyways, I think, yeah, the GPU out does improve the training time a bit. It actually improves the reading time as well, which is very interesting. I guess it probably can save some allocation of the data. So you get about 10% speed up by actually doing the copy to the GPU, right? Which is not very intuitive. So, and that would save you time during training as well, because your model doesn't have to wait for you to copy the tensors to GPU. Yeah, I didn't talk specifically about it before, but you have this slightly weird way of the output of the data. So the pipeline generates a key value dictionary again with data and label. This is hard coded from the classification iterator. There is also a generic iterator where you can specify those things. Yeah, but it will come as a dictionary anyways, which is slightly different than other data loaders. And the labels compact, so we use array here just to make a flat array. And then after this point, it's just a regular tensor, right? So this is the only code you need to change in your pipeline if you already have a PyTorch pipeline somewhere. Yeah, and that's pretty much it. So now, yeah, let's actually train something, right? Yeah, this is basically the inverted plot of what Rafael was showing before, right? You can really speed up the results, right? If you actually need to train Imagenet on a single node, it can take several days to go through the typical 100 epochs that people play with. But if you could use that training in a massive scale, you could actually have results within a few minutes, right? This has a limit, obviously. The batch size cannot be grown infinitely. As if you have a too large batch size, you're not going to have enough steps within an epoch, and the learning, it changes the behavior of the learning, basically, right? The gradients are not linear, so you can't just linear scale your learning rate. And so there are some effects, but Imagenet anyways, people generally train it of batch size 1,000 or 2,000. So you could easily have hundreds of GPUs and have a small batch size on each one of them, and still have a reasonable size. You could have a single sample per batch, per local node as well, and run on 1,000 nodes. But yeah, you generally don't need to go to that scale. It's probably, and it's also more efficient in a pricely manner to have less less nodes, because there is some loss of efficiency still, as you can see here. And when you go to very low batch size, it also takes longer to train, which we can probably explore tomorrow. We see. So let's go for the next notebook now. Let's just close this guy. And I'm now gonna use basically the same data loader that we just did before. So if you did change anything in that code, it will reflect here. Right, here we just have the imports, basically. I can collapse that. And now I want to have basically two data loaders, obviously one for training, other for validation. I'm going to do a very small model, so I will keep the augmentation in GPU, do all the decoding in GPU. That will make it much faster, and you can test that later. I have a very basic CNN here, much smaller than any ResNet. It's basically just an updated version of AlexNet. It just has some convolutional blocks, which is just a convolutional, batch norm, and C, which is also known as Swish, if you heard of that from Efficientnet. And yeah, I'm just stacking all these guys on a sequential model, and I'm using stride 2. So every block actually makes the image resolution, half the image resolution, right? Until you get to 7. And then we have a global average pool and a linear classifier on top of it. That's it, like super simple. You can see the summary here, and you actually show the output shapes as well. The image size is 224, yeah. So yeah, basic, that's it. Shows the number of parameters and yeah, the number of operations as well. And give you flops, right? If you want, you can also use the Torch vision models. Just import any model you wish, doesn't matter. Right, it's gonna work the same way. I'm gonna close this. And yeah, the train. Yeah, all right. I create this helper here, which basically has the same training loop that we did before. Right. Just to reduce the amount of code on the notebook, and just yeah, basically loop that grabs the data and the basic cross entropy loss is done in PyTorch and backwards. And then we have here some little accuracy with these running averages helpers, which are down there as well. And the validation loop, which is pretty much the same. So these functions train one epoch and then validate one epoch, right? Grab the data, which is already on GPU. So it's convenient. And then just stores the average, right? Calculate the loss from the model and so on. And here we just have this average meter, which I'm not going to go through. It just holds the average and then averages, right? This just holds the sum of all the values and the counts, and then at every step he also calculates the average, and at the end he calculates the average again. The running average is just a low pass filter with exponential moving average, right? And with a beta that you give it to. And so we're gonna use these to measure the progress. And well, we could have run this before. That's the question. Did I not commit the classifier? I'm sorry. Yeah, I can do that right now. Yes. Yeah, it's missing. Sorry. Done. Cool. Sorry for that. But you should have the file now. I thought I know I actually have it here, don't I? Delete it. No, yeah, it is here. I'm sorry. It is on this cell as well. Sorry, I had, because I collapsed the other one, I couldn't see it. Yeah, but it is generated by the cell the same way I was generating the data loader before. But anyways, yeah, I can commit that. Yeah, so all the code is here as well. So I'll steal. Yeah, and you can see the training going. This is obviously running on a single node. And your exercise now is choose what you learn or you already knew, but just do the same thing we've done before with IPC Magic, right? You have all the code here and run these on your 2 nodes. Or yeah, I don't think you can do more than 2 nodes right now with this account, right? If you wanna use your own account, obviously you can use more nodes. And then the second exercise is doing something more realistic. Normally, people don't do large scale training on the notebook, right? It's still useful to do this kind of exploration and see basically how things are working, I find. And using the right file, I find it convenient as well to share the code between this perspective and the next. But yeah, you basically wanna have a script that you can just launch your job and it runs in the background. And you're probably going to run several different configurations to test the value, and these will take some time, right? So yeah, you're not going to be waiting for to see the result. Obviously, you can do some waiting in the beginning. If your learning rate is completely wrong, you're going to notice it, right? Just by looking at the loss going skyrocketing or not moving at all. So that means that you should change your learning rate, obviously. But yeah, I would recommend doing automated hyperparameter search. It will be much more time efficient. And yeah, if you are a user of Piz Daint, you probably can afford some kind of optimization, especially using more smarter algorithms that don't need to grid search the whole hyperparameter space, right? That it's not not affordable with deep learning for anyone, I think. But there are very good algorithms around to do some more smart targeting. And we probably won't have time to cover any of that, but we can discuss that in some Q&A session if you make any. And basically, yeah, you want to convert this notebook then into a script that you can launch with the S-batch, like Rafael was showing with the benchmark, same way, right? I already posted the train Imagenet here. This is a batch script that does a setup for you. I think Rafael has a slightly different version of the setup. It doesn't really matter how you use. You just have to set up those environment variables. So here on the bash, I'm just grabbing the host name. So all this code here runs actually on the first rank, and then the environment is shared between the nodes, right? But this host name will return you the host name of the first node only, and this environment variable is going to be the same for all the ranks. But for the rank, you want that to be different on each node. So I'm evaluating that. Obviously, you could do that in Python directly. It would be as convenient. And that's it. Let's go back here. This guy. Yeah, as well, when you want to experiment with hyperparameters, it might be more convenient to, instead of having them hard-coded on your script, to use arguments passed as a CLI. And argpass is the standard solution. There are other modules they can use in Python, right? And that's an interesting way of doing your training as well, right? Without that, I mean, you can do that. You have a different code version for each one of your runs, but it's going to be very hard to do hyperparameter search like that. Basically, you want to have anyways, either way you choose, you want to have one big function that starts the training, right? So you want to have a function that englobes this piece of code. And here you're going to have all these parameters, right? For the optimizer, for the schedule. Yeah, I didn't talk about the schedule, but this is a typical schedule people use, just cosine annealing with warm up, right? Obviously, you can choose any schedule you wish. Very common is also the step decaying one. If you know how long you're going to train for, this is very efficient, right? But yeah, that's a bit out of the scope of this course. So please go ahead, and you can do the distribution down here, right? With the cluster magic. Let me stop the train. And or you can do the script, as we were saying before, right? And if you wanna skip the first part, yeah, you can just do the script directly. That's the way people use in production anyways. Okay. Does anyone has any question about any of that? Is it clear what you do? We could have a Q&A session later on, or we could leave it for tomorrow as well. It's up to you guys. All right, guys. So yeah, I guess we can check this first thing tomorrow. See if you had any issues distributing it. If you have any additional questions, data loader, the data format, how you can change your pipeline into it, whatever you think. If you want to bring your own problem, please feel free to post on this on Slack, or yeah, we can have a later session if there's anything to be discussed. Tomorrow we will talk a bit on mixed precision and have a quick look on profiling and the JIT just-in-time compiler. Nothing too much in depth, but I think it's a good overview for people that are not too familiar with. If you also have specific questions or any of that, please feel free to say on Slack or anytime, or stop us during the course as well, anytime. I guess that was it. Rafael, do you want to say anything else?
No, nothing from my side. Just thank you, and yeah, I guess see you tomorrow. No?
All right. So stop sharing. Well, see you guys then. Thank you.
Bye. Thank you.
Thank you.